It was pointed out that, yes, it is disappointing that with the exception of the geometric series, we're just figuring out whether these infinite sums add up and give us a finite number, or whether these infinite sums add up and don't give us a finite number as we add more and more terms. And so we're not actually figuring out what these series converge to, if they converge. We're just figuring out, do they converge or do they diverge? Okay, so I asked you to take a look at these two particular series, and hopefully you said, okay, well, on the first one, so let's focus on this first one. We've got the sum where n goes from 1 up to infinity of 1 over n raised to the 1 plus 1. And so I look at this example and I say, this looks an awful lot like the function f of x is equal to 1 over x raised to the 1.1. And so I might look at the integral from 1 to infinity of 1 over x raised to the 1.1 dx. Now there are three things that every single time that I use the integral test, I need to check to make sure that the function I've chosen is continuous, decreasing, and positive on our particular interval. And so here our f of x is 1 over x raised to the 1.1. And so if I draw a picture of this on my calculator, it's going to look something like this, roughly speaking. And I can see that f, so this is y equals 1 over x raised to the 1.1. F is certainly continuous on the interval from 1 to infinity. In fact, the only place where we actually have a problem is when x is equal to 0, but that's not part of our interval. So f is continuous. F is certainly decreasing. I can see that from the picture. And f is also positive. So I can check off all three of my requirements. If I cannot check off all three of these requirements, the integral test is completely bunk. I cannot use the integral test if these three requirements are not met. Which is really disappointing, because it would be awesome if we could just use the integral test at all times, because it's fun to find antiderivatives and go from there. But this test has very, very limited use. Number one, the function we choose has to be continuous, decreasing, and positive, and number two, we have to be able to find an antiderivative. Okay, so here we have our integral, and so then we can look at the integral from, well, first of all, we want to change this to a proper integral, and so we have the integral from 1 to b of x raised to the negative 1.1 dx. And so now when we take our integral, when we find our antiderivative, got the integral, well, I'm sorry. Once we take our antiderivative, we add 1 to the power. So we have x raised to the negative 0.1 divided by negative 0.1. And then we can evaluate that between 1 and b. Now, this is the crucial part, okay? We're all really good at taking antiderivatives. The harder part, in my opinion, is evaluating this limit. And so when I look at this limit, the first thing I notice is that x is raised to a negative power. So I'm actually going to fix that. Negative powers are hard to evaluate in a limit. And so I want to rewrite this as the limit as b goes to infinity of 1 over 0.1x raised to the 0.1. And now this negative sign, that's still in there. I'm just going to go ahead and tack that in on the top. That's normally where we would put it. And so I'm going to evaluate that from 1 to b. So now I'm going to go ahead and plug in my b values. My b and my 1. Limit as b goes to infinity of negative 1 over 0.1 b raised to the 0.1 minus negative 1 over 0.1 times 1 raised to the 0.1. the limit as b goes to infinity, I'm going to clean up my numeric part, -1 over 0.1 b to the 0.1. This whole fraction over here is 1. Well, -1 over 1 times 0.1. So if you clean this up, what does that whole thing look like?
10.
Yeah, that looks like 10, and we have two negatives, so it becomes plus 10. Okay, so now here's our question. So as we look at b raised to the 0.1, what the heck does that mean? Well, b to the 0.1, if we write that as a root, this is b to the 1/10, and so that's the same thing as the 10th root of b. So as b gets really, really, really big, what happens to the 10th root of b? Yeah, it's still pretty big. It's not quite as big as b, but it's still getting bigger. So as b gets big, the 10th root of b is getting big. So as b goes to infinity, the 10th root of b is also getting really, really large. So that tells us about our denominator. So our denominator is getting really, really, really big, and we're taking 1 divided by a huge number. What's happening to this entire fraction now?
0.
Yeah, it's going to 0. And so we end up with 0 plus 10, which is 10. So in the end, our improper integral converged. So the integral from 1 to infinity of 1 over x raised to the 1.1 dx converges. So by the integral test, the sum where n goes from 1 up to infinity of 1 over n raised to the 1.1 also converges. All right, so we had to do an awful lot of work to come up with that, but are there any questions about using the integral test to look at the sum where n goes from 1 up to infinity of 1 over n to the n?
What is that b to the 0.1 equals 10 through b?
So b to the 0.1, I'm analyzing what that really is, and so that's the same as b to the 1/10, and I can write a fraction power as a root.
So you couldn't exactly find out what the sequence converges on then?
That's correct. So this particular method here does not give us an answer to say that the sequence or that the series converges to a particular number. We know it converges to a number, but we don't know what it is. And that's unfortunate, but that's the best we can do. All right, other questions about this? Okay, so let's quickly look at this second series here, the sum where n goes from 1 to infinity of 1 over n raised to 0.9. And so when I look at this series, I'm still going to be using my integral test. That's what you were asked to do. And the function that we're going to look at is f of x is equal to 1 over x raised to the 0.9. Now this particular function f, if I actually draw a picture of it, and I might do this in my calculator just to make sure, but it looks an awful lot like the last function that we looked at. It may be different slopes, but the shape is roughly the same. So this is y is equal to 1 over x raised to the 0.9. And so f is continuous on the interval from 1 to infinity. F is decreasing on that interval, and f is positive. In other words, above the x-axis on the interval from 1 to infinity. So we've chosen a good f. If we cannot check off all of those requirements, we cannot use the integral test. Okay, so we're going to look at the integral. the integral from 1 to infinity of 1 over x raised to the 0.9 dx. And the very first thing is I'll make this proper, so I'll have the limit as b goes to infinity of the integral from 1 to b of x raised to the 0.9 dx.
Negative 0.9, right?
Yeah, thank you. I need that negative on there. So x raised to the negative 0.9. So after I've double checked that I made sure I did my algebra correct and I don't have to mark down illegal algebra on the board up here, okay, then I look at this guy and say, okay, I want to find the antiderivative, so I add 1 to the power. And so when I add 1 to the power here, I get x raised to the 0.1 divided by 0.1. And we're going to evaluate this between 1 and b. Now something very different happened here than the last time. In the last example, when we took our antiderivative, we still had a negative power. Whereas on this one, our power became positive. And that's going to change a lot of things for us. For example, when I rewrite this as the limit as b goes to infinity, I've got the 10th root of x over 0.1 evaluated between 1 and b. Notice that 10th root of x is in my numerator now rather than my denominator. And now I can plug in my boundaries. Limit as b goes to infinity of the 10th root of b divided by 0.1 minus the 10th root of 1 divided by 0.1. And so I'm going to clean up the numeric part of this. So I still have the 10th root of b divided by 0.1. And now I have minus 1 divided by 1/10, so minus 10. Okay. We're now ready to analyze our limit. Are there any questions up to but not including analyzing the limit? So the big deal was when we when we added 1 onto our power, when our power was a negative number and we added on 1, with this particular example, our power became positive. And so now our b is part of our numerator, and so as b gets really big, our numerator is getting large. And so that tells us that we have a huge number divided by 0.1. This term is going to go to infinity. And so now we've got a really stinking huge large number, minus 10. Well, that's still really pretty stinking big. It's just 10 less than super big. Okay? And so our final answer here is that our integral is equal to infinity.
So the reason why we couldn't rewrite that 10x because we already had a positive on the top and the other one we had a negative. So that's why we rewrote it as 1 to the x to the point, or negative 1 to the 0.1 x to the 0.1, right?
Yeah, so it's, in the last one we had this expression, because the original one was x to the negative 0.1 over negative 0.1. Is that what you're asking about?
No, just how we, I'll ask you.
Okay, all right. Okay, are there other questions? I didn't answer Dennis's question. Are there other questions?
So if we don't graph that, would you take the first derivative of that function to see if it was decreasing?
So analytically, so what we did is that we looked at this geometrically or graphically, and we saw that, and if not, if I really didn't want to draw this picture, then what I could do is take the first derivative of this function and make sure that that first derivative is always negative on the integral we're interested in. Yes, absolutely, and that would be fine as well. But no matter what, whenever you use the integral test, you always want to verify somehow that your function is continuous decreasing, and positive. And whether that's through using the first derivative or through drawing a picture, either of those are fine. But you do need to verify every time you use the integral test that these are true. Okay, so back to this example here, we have the integral, we had our integral from 1 to infinity of 1 over x raised to the 0.9 dx. This integral diverges. So by the integral test, the series, which is the sum where n goes from 1 up to infinity of 1 over n raised to the 0.9, also diverges.
Can we leave like an n in there, or do you want us to change it to x all the time?
So change to x in the same way that when we worked with sequences, we changed n's into x's for derivatives, just because the x represents a continuous function, whereas the n is just a bunch of dots.
Okay.
So on the test, we get counted off. We just decided to, since we saw it was infinity, could we just write out the sum of, n equals 1 to infinity diverges instead of writing out the infinity?
So you're not wanting to write this entire sentence at the end of your conclusion. So a couple of things. First of all, on an exam, I'm going to ask you to specify which test you've used. So somewhere in there, I want to see the words integral test. And so if at a bare minimum, if you had you evaluated your integral, and then you wrote integral test, and you wrote that this series diverges, that would be sufficient, along with the work to show the integral. So yeah, you could cross that part off, and that part if you want to be minimalist.
How come we couldn't rewrite that other side, like 0.1x to the 0.1?
This one here?
Yeah.
Wait, so how would you like to rewrite it?
Like you did the other side. Like the first problem.
Okay, so how are you thinking?
Or wouldn't it be just 0.1 divided by 0.1x to the 0.1 power? Could you write it that way?
0.1 divided by
0.1x.
like this?
Yeah.
So this is our power. So what we had last time was that we had x raised to the negative 0.1 divided by negative 0.1. So this negative 0.1 will stay in the denominator. And because there's a negative power in the numerator, that's going to drop into the denominator and change the power to positive. And our numerator has nothing left but a 1 in it. Now on this one, my constant here will stay in the denominator. But my power in my numerator is positive, so I'm not going to switch this into the denominator. If I did, I'd have to put a negative on the power to move it down there. So I'm going to leave this guy in the numerator. So I actually didn't really do any rewriting at all. Okay. All right, other questions? Okay, so something that you might have noticed here is that I chose two numbers, 0.9 and 1.1, are numbers that are very close to 1. Just a little bit to one side of 1 and a little bit to the other side of 1. Okay, so the focus here is that power up here, the 0.9 or the 1.1, make a big difference on whether your series is going to converge or diverge. And so last class, we looked at our very first example using the integral test. Well, actually, our second example. We looked at the sum where n goes from 1 up to infinity of 1 over n. And this was a very, very special series. It has a name. It's called the harmonic series. And there's no power on this n, but if I wanted to, I could think of the power on this n as a power of 1. We just don't write that down. And so we can think of this as the sum of 1 over n raised to the first power. Okay? And so that's our harmonic series. And we showed last time that the harmonic series diverges. And we used the integral test to show that. Now it turns out that this power of 1 up here is exactly the dividing line. And so if your power is greater than 1, you're going to have one result. And if your power is less than or equal to 1, you're going to have a different result. And so a consequence of the integral test is something called a p-series. And a p-series is a series that looks like the sum where n goes from 1 up to infinity of 1 over n raised to the p. So if I were to write out terms in this series, okay, I need to be really careful here because I have two letters going on in this series. Okay? The letter that is incrementing is the n, and the p is not incrementing, so that remains as a constant value. And so it looks like I would have 1 over 1 to the p, plus 1 over 2 to the p, plus 1 over 3 to the p, plus 1 over 4 to the p, plus dot, dot, dot. Now, our three examples that we see here are our harmonic series, as well as the two examples we just looked at, are examples of p-series. And so the sum of 1 over n is a p-series with p equal to 1. The sum of 1 over n raised to the 1.1 is also a p-series, but with p equal to 1.1, p being the power. And our last example that we looked at was the sum where n goes from 1 up to infinity of 1 over n raised to the 0.9, which is a p-series with p equal to 0.9. So these are three examples of p-series. So what we're looking at here are series where the n is part of the base and the power is a fixed number. Okay. Compare that to a geometric series where the base was a constant value and the power was the thing that was incrementing. Okay, so very different from a geometric series. Okay, so on these p-series, the base is incrementing, n goes from 1 up to infinity. The power is remaining constant.
It's just inverse in the geometric series.
That's exactly right. The geometric series is exactly the opposite. Base remains constant, power is incrementing. Okay, so when I look at these numbers, on the first one, the series diverges, and we showed that by using the integral test. In the second one, when p was equal to 1.1, that series converged. And when p was equal to 0.9, the series diverged. And it kind of makes sense based on the examples that we did. If this power was less than 1 down here, then when we took our antiderivative, our x ended up in the numerator. And if our power was greater than 1, then our x still remained as part of our denominator. And so from the integral test, we can say the following. So on a p-series, if p is greater than 1, then the sum where n goes from 1 up to infinity of 1 over n to the p converges. If p is less than or equal to 1, then the sum where n goes from 1 up to infinity of 1 over n to the p diverges. All right, so this makes life super, super easy. So for example, look at the sum where n goes from 1 up to infinity of 376 divided by n raised to the third power, I can look at this series right here, and it almost looks like a p-series, except for that 376 in the numerator. So what could I do to this to make it look just like a p-series? Yeah, that's a constant up there, and it's in every single term of our series, so we can factor that out into the front. And so we can write this as 376 times the sum, where n goes from 1 up to infinity of 1 over n to the third. And as soon as I write that down, then this part right here, the sum of 1 over n to the third, this is a p-series, with p equal to 3, and 3 is certainly greater than 1, and so our series converges. And that's way quicker than doing an integral test. All right, are there any questions about that?
So on the test or whatever, can we just say converges with p-series test or what?
Absolutely. So you can. So if you can rewrite this and say, hey, look, this looks just like a p-series. You can say p-series. You should identify what p is equal to. Say, okay, p-series, p equals 3. 3 is greater than 1. Series converges. Done.
I not do
You do not have to do the integral test.
Nice.
And I think the p-series will always follow that form of 1 over n to the p.
That's correct. Yes. Yes. So every p-series is of exactly this form right here.
Okay, so we won't see something to like 2 negative exponent that actually is in that form and we have to go through.
So yeah, so you might have something like, so I guess we should say, okay, consequence of the integral test is this p-series where p is a number greater than 0, so some power, some positive power.
Okay. You would give us like n raised to the negative 3 and then times, you know what I mean? Like,
Yeah,
when-
well, so you're right. I mean, we're going to look at series that are going to convolute things a little bit. So we will see some of those. It's maybe not quite as bad as you're thinking in your head, but we will see some that are a little convoluted. Other questions? Okay. In that case, I would like to open up the floor for the last 10 minutes before the break for any questions that anybody has in section 8.2. So 8.2 was geometric series and also the divergence test. Alex?
Can you do 15 out of 8.2?
Yes. Oh, that's 8.1. Let me look in the right section. Well, 1 plus.
Oh, no, that's not it.
To the end of our 3CN. Alex, is this one you're looking at?
No, the one I'm looking at is the sum of NE to the N.
Change
Did I
that.
build it down? Well, that is A3, my apologies. Never mind.
Oh, okay. Okay, alright, so I'm gonna erase this one from 8.2, that was from 8.3, so I'm gonna wait until next time to answer that question.
Sounds like a plan.
Okay? Alright, so, Chad?
Number 35.
Okay, number 35.
Yeah.
That's the bonus question.
Okay.
So I'm not gonna take time in class to work on that one. Stop by office hours for that one. Okay. Number 39, okay.
39 seemed like an illegal controversy step got made there.
This is
Alright.
on 8.2?
Yeah,
This is 8.2, number 39.
that's not how you find God.
So what is going on here? Okay, so we've got something that looks like 0 is equal to 0 plus 0 plus 0, and we have an infinite number of zeros all added up together. And so then this person, this mathematician, well, pseudo-mathematician, said, okay, well, 0 is equal to 1 minus 1, so I'm going to write this as 1 minus 1 plus 1 minus 1 plus 1 minus 1 plus dot dot dot. And so totally legit, right? I mean, 0 is equal to 1 minus 1, so we can do that substitution. And so now we've got something that looks like 1 minus 1 plus 1 minus 1 plus 1 minus 1 plus dot, dot, dot. All right, great. So we've gotten rid of the parentheses, and oh look, if I reintroduce the parentheses, I can reintroduce these parentheses as 1, well let's see, I guess I would have to do this as 1 plus negative 1 plus 1 plus negative 1 plus 1 plus negative 1 plus 1 plus dot, dot, dot. And so now it looks like we have 1 plus 0 plus 0 plus 0 plus dot, 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 which suddenly means that 0 is equal to 1. Alright, so we have just shown that 0 is equal to 1. Okay? And that's great, except that it's not quite valid. So there's something funny going on here. Becky, did you have any thoughts on why this might be funky? Okay, so you know, this really does look very legitimate at first glance.
Why are we accounting for the last one that's not in there? Because we don't worry of parentheses, because you shift the parentheses over, that means that it's going to have negative 1 plus blank at the very end, right?
But there is no very end.
It's infinity.
This sum goes on forever and ever and ever.
Well, yeah, but you shifted the parentheses over. There's got to be a number that's odd on the other end also.
You keep using the word other end. There is no other end.
Oh, come on, don't get hung up on semantics.
So yeah, so you're right. I mean, if there was a stopping point on these series, then you're right. We would have this problem with this extra 1 that didn't have a partner at the end, and that would be a problem. But because these sums are infinite, there is no other end to stop and say, okay, we're going to stop here. Now, here's the problem with this. And the problem comes into this step right here in the middle. Now, it turns out that if you are looking at two different infinite sums, okay, so in our first example, if we have the sum of all the ANs is equal to 0 plus 0 plus 0 plus 0 plus dot, dot, dot. I guess really what I'm saying here is that this is the sum of a whole bunch of zeros where n goes from 1 up to infinity. Okay. Now when I add up 0 plus 0 plus 0 plus 0, I still get 0. Now this other way of writing the series as 1 minus 1 plus 1 minus 1, what that series really is the sum where n goes from 1 up to infinity of negative 1 raised to the, I guess I could raise to the n plus 1. So I have a positive number for when n equals 1 and a negative number when n equals 2. And so I have 1 minus 1 plus 1 minus 1 plus 1 minus 1 plus etc. And playing around with the parentheses is just a red herring. Okay? These two series are actually very different. And the reason is because what you want to remember is something that gets kind of swept under the rug when we talk about series. When we talk about series, what we're really doing is looking at an infinite sum of numbers, but the way that we analyze these guys is by first looking at the first term in the series, and then looking at the first plus the second term, and then the first plus the second plus the third term, and the first plus the second plus the third plus the fourth term. And we want to add on one term each time that we move over. Now in this first series, the sequence of partial sums is, okay, so let's take a look. If I just add the first term in the series, I have a 0. If I add the first plus the second term, what's 0 plus 0?
10.
That would be incorrect. First plus the third, second plus the third term also gives us series. First plus the second plus the third term also gives us 0. And so our sequence of partial sums is a list of zeros, which tells us that the series converges to 0. Now let's look at our second one down here. Our sequence of partial sums let's see, if I just add the first number in our list, in our sum here I have a 1. And if I add the first plus the second number, what do I get then? 0. And if I add the first plus the second plus the third,
1.
I get 1. First plus the second plus the third plus the fourth, 0. And so my sequence of partial sums is alternating between 0 and 1. So when we have a sequence that bounces between two numbers, will that sequence converge? No, that sequence diverges. So the sequence of partial sums diverges, so our series diverges. And the reason that, and so these two infinite series are in fact very different. Okay? And the reason is because our normal understanding and intuition, some of that can stay with us, but some of it goes out the door. So like Will's suggestion of the intuition of there's going to be this extra 1 at the end that is not going to match up with everything else that's going to be stuck outside the parentheses, and that minus 1 is going to cancel this 1 at the beginning. Well, when you're talking about an infinite series, there is no end. And so that piece of intuition gets thrown out the door, and we have to rely on the definition of a converging sequence, or a definition of a converging series, which is that we look at the sequence of partial sums and see what happens. And so the steps that debunk us here are these ones in the middle where, yeah, we've regrouped, but it's this middle guy right here is not the same as the line up above in terms of infinite series.
So what we would say, what is wrong or not?
So what we would say is wrong is that by regrouping these guys and then saying that we're going to always consider terms in pairs, that's not how our sequence of partial sums works. We always add one term on when we're looking at a sequence of partial sums. And here they're trying to group two numbers together. And so that's what's going on. That's what's wrong with this.
So they're just grouping two numbers instead of just adding it.
That's right. That's right. And so by grouping two numbers, what they're doing is that they're looking at every other one of these terms in our sequence of partial sums. And that's where things are illegal. All right. Any questions or comments about that?
So there really is no God?
So that is up to you. But you can go and mess with your friends at your party on Friday night and show them this and just sweep the cheating part of the road. Okay, so let's stop here. Please take a 10-minute break. Each day we kind of talk about a new integration technique, and you had some practice on those integration techniques, and that was great. And if I went and said, okay, use partial fractions on this integral, then everybody could go and use partial fractions. If I said, use integration by parts on this integral, everyone could go and use integration by parts on that particular integral. The issue came in when you were walking down the street and an integral jumped out from a dark alley and didn't tell you what integration technique to use. And so that's where problems came in. And a similar thing is going to happen here. I mean, we are filling up our toolbox for figuring out whether a particular series converges or diverges. And we're going to continue to add some more tools onto this. But before we continue to add some more tools, I'd like to summarize where we're at right now. So right now, here are some series tests that we know. And I'm going to write these in kind of, in my opinion, a good order to sort of analyze the series. And sort of, you're walking down the street, the series jumps at you from a dark alley. Here are sort of the things you want to throw at the series, maybe roughly in this order. So the first thing you want to look at is your test for divergence. And remember last time when we talked about the test for divergence, so series tests we know we're looking at the sum of all the ands. The test for divergence says that if the terms of the series do not approach 0, then the sum of all the terms diverges. So the very first thing I might want to do when this series jumps out from the dark alley is say, let me look at the terms. I want to cover up the sigma, I want to cover up the summation, and say, let me look at the terms. And are these terms, as a sequence, is the sequence of terms converging to 0? If the answer is no, if they're bouncing all around, or if the terms are going off to infinity, then automatically my series diverges. So that's the very first thing I want to look at. The next thing that I want to look at is another easy test, and that's the test we just learned, the p-series test. And so when I look at a p-series, I want to ask myself, okay, does my series look like a p-series? And some things that I want to look for is the n a base rather than a power? And is the power a constant value? And so I need to be able to identify if the power is constant, that's my p, then is p greater than 1 or less than 1. Okay. But that's a pretty quick test for me to look at. So I'm looking at series that are of the form the sum of 1 over n raised to the p. All right, so another one that I might look at after the p-series is, I might look at this and say, okay, do I have a harmonic series? And so the harmonic series is kind of just the opposite of the p-series. The harmonic series has n in the power, and the base value is a constant. These are things I want to think about with a geometric series. And I'm missing one test up here. Which one have I not written down so far?
Integral.
Yeah, the integral test. And I want you to notice that I'm putting the integral test as very last on the list. Very last test is the integral test. And the reason that I'm putting the integral test last on the list is that the integral test is super, super useful to prove that the p-series is valid. Once we have the p-series, that takes away most of the reason that we ever want to use the integral test. There are very, very few integrals where we actually need the integral test to find an answer. And so with the integral test, the thing we want to ask is, can we find an antiderivative and is the associated function continuous, positive, and decreasing? Okay, so these are all of our tests thus far. We have 4 tests: the test for divergence, p-series, harmonic series, and integral test. And so what I have for you right now is 4 examples of some series that live in some dark alleys. And I would like for you to defend yourselves against these series, and I'd like for you to have at least a partner in this class to defend yourself against these series. So please look around at the people around you and determine who it is that you'd like to work with for the next 10 to 15 minutes of class. Yeah, I don't know what I was thinking. My brain had a brain gasp in there. All right, you should now be ready to enter into this dark. So the terms and so these are our terms, which means we're thinking about a sequence. And so I can look at these terms and notice that my power on the top is smaller than my power on the bottom. So the terms go to 0. So my terms are going to 0, which means that I know nothing in terms of the test for divergence. Test for divergence says if our terms do not go to 0, then our series diverges. But if our terms do go to 0, then we know nothing. All right, so we know nothing so far. All right, so then some other suggestions and some other ideas that folks are working on is, oh, we might be able to look at something with the integral test here. And so because my geometric series, there's no n in the power, so it's certainly not a geometric series. Maybe a p-series, but it's not quite in the form of a p-series. There's this +1 down here, but it kind of looks sort of like a p-series. We're going to come back and talk about that in a minute. But because it does not look exactly like a p-series, algebraically, no, I cannot write this as n squared over n cubed plus n squared over 1. That would be illegal algebra, okay? Because I have a plus sign in the denominator, I cannot split this up. Okay, so we go on to the integral test. Now, with the integral test, I'm looking at a function that looks like x squared over x cubed plus 1. And when I graph this particular function, it looks something like this. And so there are some problems with this. First of all, f is not decreasing. Okay, I've got this hill here at the beginning, but if I draw a line, then everywhere from that line over, f is decreasing.
Is that line at x equals 1?
No, actually x equals 1 is somewhere over here, I think.
So it doesn't have to meet your starting value.
That's exactly right. So I put a little asterisk on our integral test that the f decreasing must be from some value and on. It does not have to happen right at the starting value of our series. Okay? So as long as f is decreasing from some point and on, then we're okay. All right, so f is decreasing, f is continuous, and f is positive. And so from there, you have a bunch of work to do. You've got to analyze the improper integral, probably going to have to do a u substitution and work through it that way. But I just wanted to get you started on this particular part. Are there any questions about this? Okay, so what I'm hoping is that you're starting to get a little annoyed with the integral test. Because the integral test requires a lot of stuff. You have to verify that your function qualifies under these three conditions, and then you've got to evaluate an improper integral, and you've got to do all of this stuff. And it's a fair amount of work. Okay? Now, something that you might observe, and at least one group did observe this, is that the sum, as n goes from 1 up to infinity, of n squared over n cubed plus 1, well, if I do a little bit of shady math here, if I just kind of cover up that plus 1 right there, then if I simplify this thing and kind of cover up that plus 1, then this looks an awful lot like n squared over n cubed. And so in particular, for large values of n, this plus 1 doesn't matter at all. And so for large values of n squared over n cubed plus 1 looks like, well, it looks an awful lot like n squared over n cubed. I mean, that plus 1, if you're talking about a million squared over a million cubed, that plus 1 is not going to make any difference to us in the world. And so this term looks an awful lot like n squared over n cubed, which if you simplify it is 1 over n. And so when I look at this series up here, it kind of looks like the series, the sum of all the 1 over n's. And so we would expect the sum of n squared over n cubed plus 1 to behave in way that the sum of 1 over n behaves. Now we know an awful lot about the sum of all the 1 over n's. That's our harmonic series. It's also p series with p equal to 1. So the sum of 1 over n is the harmonic series. And the harmonic series diverges. And so since we know our harmonic series diverges, we would expect that our mystery series would also diverge. And so this idea of saying, oh, well, this series looks an awful lot like a known series is our next test that comes along. It's called the limit comparison test. So here's what the limit comparison test says. And this is in section 8.3. Limit comparison test is used to determine if the series, being the sum of all the ANs, converges or diverges. Now, one requirement for the limit comparison test is that the terms are always greater than 0. Now, what we're going to do for the limit comparison test is we're going to choose a series, which will be the sum of all the BNs, where we know if the sum of all the BNs converges or diverges. All right, so here's how our limit comparison test is going to work. We have a mystery series, which is the sum of all the ANs, and we're going to choose in a clever way a second series, which is going to be a known series. And then we're going to compare our two series, and whatever happens with the known series is going to happen with our mystery series. Okay? Now, it's a little more precise than that, and here's the precision. It says if the limit as n approaches infinity of the mystery terms divided by the known terms is equal to c, which must be greater than 0. So if the ratio of our mystery terms over our known terms is equal to some number, not 0, then the mystery series and the known series both converge or both diverge. Now, as a note below the limit comparison series, or limit comparison test, often the known series, the sum of all the BNs, is a p-series. Okay, so let's look at our example. Number 4 on the sheet you were just working on with your group. If you were working on it as a group, you didn't know the limit comparison test, so you probably used the integral test. We're going to use the limit comparison test to look at this series. So we have the sum of n squared over n cubed plus 1, where n goes from 1 up to infinity. All right, so now I've got this series and I look at it and I say, well, this series kind of looks like a P series, but not exactly. And so I'm going to cover out my series symbol, and I'm going to look at my terms. And so my terms are n squared over n cubed plus 1. And from these terms, I'm going to look at the dominant term in the top and the dominant term in the denominator. So, identify the dominant terms in the numerator and the denominator. So that means that I'm looking here at the numerator. The highest power in the numerator is the n squared. The highest power in the denominator is the n cubed. So I'm going to just look at those dominant terms and ignore all the lower powered terms that are going on here. And so here's how I'm going to choose my known series. My known series is going to be the sum of n squared over n cubed. So I've taken my two dominant terms, and I'm going to look at this series. Now I want to simplify this a little bit, so this is the same as the sum of 1 over n. Alright, so I look at my known series, the sum of all the 1 over n's, and I say, oh look, this is a P series where P is equal to 1, or I could say, oh, this is the harmonic series. So, harmonic series, and this series diverges. Alright, so the very first thing that I need to do in the limit comparison test is choose a series where we know whether the series converges or diverges. Our choice, our known series, is going to be the sum of all the 1 over n's. Okay, so after I've chosen that known series, I need to do this analysis. My limit analysis is saying, hey, you know what? My choice for the known series is a good choice. It's comparable with our mystery series. So this comparison, this limit comparison, will be the limit as n approaches infinity of the mystery terms divided by the known terms, the a_n's over the b_n's. So we'll have the limit as n approaches infinity of n squared over n cubed plus 1 divided by 1 over n. So I've taken my mystery term divided by my known terms, and now I need to do some simplifying. So I've got the limit as n approaches infinity of n squared over n cubed plus 1 divided by 1 over n. I can multiply by the reciprocal. And so we've got the limit as n approaches infinity of n cubed over n cubed plus 1. Okay, are there any questions about what I've done so far? Okay. So I'm still looking at this limit. Now, this is a limit of a bunch of terms, so this is a sequence type thing. So in order to, I can now use my sequence tools for limits. So I can either look at highest powers or I can use L'Hopital's rule. Highest powers is preferable because we have a lot less work to do. And so looking at the highest power on the top and the bottom, we have 1 times n cubed in the top and 1 times n cubed in the bottom. So our limit is equal to 1. Okay, this number that I came up with at the end, let's look back at our limit comparison test. It says, all right, if we take our mystery terms divided by our known terms, and we get a number that's not 0, that tells us that our known series was a good comparison choice. So this limit calculation is showing that our known series is a good comparison. So our final limit's equal to 1, which tells us, so 1 is a number greater than 0, tells us that the sum of 1 over n is a good comparison with our mystery series, sum of n squared over n cubed plus 1. So I guess I should say since the sum of 1 over n diverges, then by the limit comparison test, which I'm going to shorten to LCT, by the limit comparison test, the sum of n squared over n cubed plus 1 also diverges. Alright, so before I told you the limit comparison test, we looked at sort of the idea of why this series might converge or diverge. And the reason is because it looks an awful lot like this P series that we already know. So the limit comparison test has 2 major steps to it. The first step is identify a known series, number 1. Number 2, convince everyone that your known terms and your mystery terms are in fact comparable by calculating this limit and coming up with a number. Okay, so this is the limit comparison test. I'll give you a couple